Yeah, good morning. So in last class, we have discussed about the polar plot, and today we discuss about the Nyquist plot analysis. So the concept of this Nyquist plot is based on the polar plot only, because which can be we can conveniently apply the stability analysis of any kind of system. Before going to Nyquist plot analysis, we need to have the polar plot analysis. Then only you can go for Nyquist plot analysis. So this Nyquist plot is divided into 5 steps. Divided into 5 steps. So each step we need to understand before going to the Nyquist plot analysis. So what is the step one says? Here is we need to understand pole zero plot, pole zero configuration. I can say pole zero configuration from Nyquist plot point of view. We have studied pole zero configuration. That is, if the closed loop system, if we have that is C of S by R of S, the denominator is equated to 0. The roots of that denominator is called as poles of the closed loop system. Likewise, in the Nyquist plot point of view, how this pole zero configuration is given. So from Nyquist plot point of view. Then second step is concept of encirclement. So concept of encirclement that we discuss, and number of encirclements and number of encirclements. And third step is analytic function and its singularities and the fourth step is mapping theorem, or we can say Cauchy's principle of argument, mapping theorem or Cauchy's principle of argument. When you understand these 5 steps, it will be easy for plotting the Nyquist plot. Principle of argument, and finally Nyquist stability criteria. So these are the 5 steps which you have to understand before going to the Nyquist plot analysis. So we have given separate this complete Nyquist plot as separated into 5 steps. So first and foremost is pole zero configuration. So that we study here now. Pole zero configuration. We have studied that any function can be written in the form of polynomial equation in the numerator as well as in the denominator. Say for example, if I have given a function f of s, that is polynomial equation in the numerator and the polynomial equation in the denominator. If I equate to 0, then the roots of that q of s equal to 0 will become the poles of this f of s. And if it is equal to 0, then we studied that the numerator equal to 0, the roots of that p of s equal to 0 equation are called as zeros of f of s function. Likewise, we consider a function that is open loop transfer function. Consider the open loop transfer function. What is that? G of s into h of s is equal to, we can say it is open loop transfer function. So we have taken this open loop transfer function, and this open loop transfer function can be written as in terms of numerator and denominator. Okay, so if it is, say for example, p of s by q of s, then the roots, the poles, q of s equal to 0 and p of s equal to 0, then we can say the roots of the denominator, that is the poles, we can call it as poles, roots of the denominator, we can call it as poles, or we can say another name is open loop poles. We can say because it is open loop transfer function, so open loop poles. Okay, and similarly, if the roots of the numerator, we can call it as open loop zeros. Open loop zeros. So that's what we have. We can consider this open loop transfer function, and then we can find out the open loop poles and open loop zeros. Similarly, if I take the closed loop transfer function, that is C of s by R of s, which is equal to G of s by 1 plus G of s into H of s. So here, this is the polynomial equation in variable s, and also this is also one of the polynomial equation in variable s. So if I equate to 0 and if I equate this 0, then I'll be getting closed loop poles and as well as closed loop zeros. Closed loop poles and closed loop zeros. So the poles of this transfer function is nothing but, if you take this this one, we can say poles of the closed loop transfer function is nothing but, what do you say, roots of characteristic equation. Roots of characteristic equation. What do you say? 1 plus g of s into h of s equal to 0. That is called as characteristic equation. So that is, we can say, closed loop poles of the transfer function. Closed loop poles. Whereas in this case, we have talked about it is open loop poles. So closed loop poles of the closed loop transfer function. So which one? The roots of this characteristic equation. Roots of this characteristic equation. So now, if you take this g of s into h of s, one example, if you take, so the roots of this, the 1 plus g of s into h of s, if I take mathematical, if characteristic equation as in terms of f of s, if I take, that is 1 plus g of s into h of s. If I this itself is take that function, if I take the function, so here this is not is taken as equation. This is not taken as a equation. We should not take this as a equation. It is a function in variable s. In variable s. I'm not taking this as a characteristic equation. So I'm taking this as f of s. I'm taking this as f of s is equal to 1 plus g of s into h of s. That is equal to, if I write p of s by q of s, means this itself is having the numerator and denominator. So if I equate to 0 and if I equate to 0, then I'll be getting the roots of this denominator and roots of numerator, which are called as poles of this f of s and zeros of this f of s function. That's what we discussed in the beginning. So now roots of this p of s equal to 0, I mean roots of p of s equal to 0, if I find, what you call this, we will call as zeros of the function f of s. It means the function f of s means what? 1 plus g of s into h of s. Similarly, roots of q of s is equal to 0. We can say the poles of which function f of s, that is poles of 1 plus g of s into h of s. Here this whole thing I have considered as a function f of s. 1 plus g of s into h of s I have considered as f of s. It is not the equation, please keep it in mind. Open loop poles of a system. Open loop poles of a system. So we take some examples. Say for example, I have taken g of s into h of s, which is equal to 10 by s into say s plus 2, if I have taken. So if I take the poles of 1 plus g of s, 1 plus g of s into h of s is equal to, this will become 1 plus 10 by s into s plus 2. So which is nothing but s square plus 2s plus 10 divided by s into s plus 2. So this has become this f of s. This is I have taken as f of s. So this f of s has become as numerator and as well as it has a denominator, right? So if I equate to 0, this is called as poles of this f of s. So what are the poles of f of s? Poles of f of s is equal to s is equal to 0 and s is equal to minus 2. Similarly, this is what you can say open loop transfer function. This is what you can say open loop transfer function. So what are the open loop poles here? Open loop poles, nothing but, if I equate the denominator of this open loop transfer function equal to 0, s is equal to 0 at s equal to 0 and s is equal to minus 2. So if you look at here, this and this are same. It means that poles of f of s, poles of f of s is equal to open loop poles of the systems. That's what I have written here. That's what I have written here. So poles of 1 plus g of s into h of s will become the open loop poles of a system. So that is which I have explained with the example, that is open loop transfer function is given as g of s into h of s 10 by s into s plus 2, where if I find the poles or open loop poles of this particular open loop transfer function equal to 0, so s is equal to 0 and s is equal to minus 2, I am going to get the roots. So these roots are called as open loop poles. Similarly, I have taken f of s, I have defined f of s as 1 plus g of s into h of s. So I have taken 1 plus 10 by s into s plus 2. So this will become, the numerator will become the, in terms of p of s, and it is going to be q of s. And equal to 0, you can get the poles of f of s. You can get the poles of f of s, that is poles of 1 plus g of s into h of s. So poles of 1 plus j of s into h of s is equal to the open loop poles of the system. So this is what we can conclude from the above example. Right. So now zeros. Now we can consider zeros of 1 plus g of s into h of s. 1 plus g of s into h of s. So zeros of 1 plus g of s into h of s can be taken as, this is closed loop poles of closed loop poles of system. Why? Because see, if I take the g of s into h of s, which is taken as closed loop poles, c of s by r of s, which you can write as c of s by r of s, is equal to g of s by 1 plus g of s into h of s. One plus g of s into h of s is nothing but the 1 plus g of s into h of s, that is nothing but s into, I mean, s square plus 2s plus 1 we are going to get as a zeros. We are going to get as a zeros of the system. So what is the 1 plus g of s into h of s? If I have g of s into h of s is like this. So if I get this, this will become s square plus 2s plus 10 equal to 0. So 1 plus g of s into h of s will become, so this is equal to 0 means the roots of this equation, we can call it as closed loop poles. Similarly, this numerator, that is p of s of this f of s, if you look at here, the p of s of this s square plus 2s plus 10 will become the numerator for the f of s function. It means that the zeros of this f of s, zeros of f of s. So zeros of 1 plus g of s into h of s is nothing but s square plus 2s plus 10 equal to 0. And similarly, if I take this g of s by r of s, which is g of s by 1 plus g of s, if I equate the characteristic equation to 0, that is 1 plus g of s 10 by s into s plus 2, that will become s square plus 2s plus 10 equal to 0. So that is nothing but closed loop poles. So that is why closed loop poles of a system. So from the f of s, function, that is, we can conclude that poles is nothing but, we can conclude 2 points here from the above. One is poles of 1 plus g of s into h of s. Poles of 1 plus g of s into h of s is nothing but equal to the open loop poles, nothing but open loop poles of the system. So we can take the poles of 1 plus g of s into h of s, that is nothing but equal to the open loop poles of the given system. If I want to have the zeros of 1 plus g of s into h of s, then that is equal to the closed loop poles of the system. Closed loop poles of the system. So this is very important conclusion from these two example. So it we can say from the Nyquist point of view, the system is absolutely stable. If the Nyquist point of view, Nyquist Nyquist plot point of view, I'm talking Nyquist plot, point of view. What is talking about is the system is as we know that when it lies on the left hand side, right? So left hand side of the S plane, generally we'll say that absolutely stable, absolutely stable. So the system is absolutely stable if all zeros of if all zeros of 1 plus g of s into h of s. In zeros of 1 plus g of s into h of s is nothing but closed loop poles of the system. Means poles are lying on the left hand side. When we say poles are lying on the left hand side, then we can say the system is absolutely stable. Absolutely stable. That is, if all the zeros are located in the left side of or left half of left half S plane. Means as we discussed in the so when the poles are falls on this left side, when the poles falls on this left side, then we can say the system is stable, absolutely stable. So the stability area will be remain same for both what you call same, only the way expressions, as we told that in the previous examples, all the poles which are lying on the left hand side. So whereas in this case according to which is called as Nyquist criteria, we are going to analyze, we are going to express the analyzing this function of 1 plus g of s into h of s. We are expressing this in terms of by using this function, that is 1 plus g of s into h of s. So that's what we have discussed. This is the poles of this is nothing but open loop poles, and zeros of this is nothing but closed loop poles, So this is about the pole zero configuration from the Nyquist plot point of view. Okay, so poles are nothing but open loop poles, zeros are nothing but closed loop poles of the given system. So we are taking into consideration is f of s, that is 1 plus g of s into h of s, and then based on that we are going to study the stability analysis. This is the first part of Nyquist plot analysis. Now we'll move to the encirclement. Second step which we have discussed here in this is the second step, that is concept of encirclement and number of encirclement. So that we discuss here. Concept of encirclement and number of encirclements. Right. Here, what we have discussed is enclosement. Means if here the points are enclosed, means that polar plot which I have discussed here. Say for example in this, the point. Say for example here, if it is lies, then it is enclosed by this polar plot. If the point is lies here, then we can say it is not enclosed by the polar plot. It is outside this path. Okay, similar to that, we are going to study the encirclement. So here it is applicable, this encirclement, which we call, say for the polar plots which you have discussed, the closed path. This is a open path, we can say. This is open and not closed like a polar plots, because it is a like this. Okay. Now, but for a closed path, it is very necessary we have to understand this concept of encirclement. So if I take the closed path, if I take any closed path, say for example, if I have taken it is a path is, say for example, about the origin, I have rotated like this, I have taken, and this completely it is about the origin, and I have taken a point where A is here. So, and this is what we can say a new path which is called as tau of S. So in this, the points, the O and as well as A, these O is the origin, we can call it as O is the origin, and the point A, both points are enclosed by this circle, enclosed by this path, enclosed this by path. So, or we can say encircled by this tau of S path, encircled by this path. So where this is real axis and this is a imaginary axis, and these 2 points. So this is what we can say closed path. We can say it is a closed path where all the points are lying inside this path. We can say it is encircled. If it is lies outside, then we can say outside of this, it's not encircled. It's not encircled. Say for example, the point B is here, then it is not encircled. So here, it is always we need to count the number of encirclements of this of a particular point. See how many encirclements of this particular point A we need to find out. How to count either A or O. So counting number of encirclements. How to count this number of encirclements? That's we discuss now. So if I say the number of encirclement for this previous figure, which you can say it is only 1, right? Because there is only 1 encirclement. So that is point A, and point O is 1 in anti-clockwise direction. The direction is also very important here. So the direction is this encirclement of this A is only one in anti-clockwise direction. Anti-clockwise direction. Okay. So similarly, if I take even for the O also, even for the O also, there is only one. There is only one encirclement. Only one encirclement for this point A. So how to find this encirclements? If I draw a closed path, arbitrary closed path, I am just taking, okay. So I have taken like this, and these points which you have to draw in any orientation. In any orientation, if you draw, say for example this orientation, and A is drawn this orientation. So if you draw in any orientation, that is vector. So if it touches a point, if it touches a point on the path, that is this point and this point. So here this line is touching this tau of S closed path at once. So at one particular point, and also here the direction also to be shown. This is anti-clockwise, and this is also anti-clockwise. So here for the anti-clockwise, we will be showing with plus. Anti-clockwise will be showing with plus, and clockwise will be taking as negative. So how many points, how many times it is touching this tau of S closed path? Only once. This is also only once. That is why the number of encirclements for point A is taken as 1, and number of encirclements for the point O is taken as 1. So this is how we can find out the number of encirclements. Similarly, if I take one more path where suppose if I have a path consists, say for example like this and like this and like this. So here if I have taken a points, here I have taken a points A and O. Say here is the A and here is the O, and the direction is also very important here. So you can take this is the direction, and then like this. Okay, so now you can take any orientation of this A like this, okay, and say this is origin O. So you can take like this. Okay, so if you look at this, this point is cutting at two this one and plus this one. So it is nothing but it is encircled by 2. Means one is the direction is also to be taken. See here how which is direction is, it is in a clockwise direction, and this point is also in, this point is also in clockwise direction, this point is also in clockwise direction. So there are 2 directions you got. So that is clockwise direction minus How many are there? 2 arrows are there. So then it is encircled by 2. So where the number of encirclement will become -2. Similarly, this point and as well as this point. This point is also having in this clockwise direction only, and here is also the clockwise direction only. So here a clockwise direction in the sense negative. First direction negative, then number of directions here counted is 2. So it will become n is equal to -2. N is equal to -2 for the A and O as well. And one more path, if it is represented, say for example, so this is O and say this is A, and I have a path where it touches like this and goes and like this, and it goes, means this is the closed path which I have for plotting a plot. Then we need to know how it can be. So directions also to be mentioned here. So the directions is like this, and this one is like this, and this one like this, right? So now you need to draw with any orientation like this, or it may be like this. So for O I have drawn like this, and A I have drawn like any orientation. It may be any orientation, and all, and here it is touching. Say first this is 1, and then say this is 2. So first one is in what direction? It is in a anti-clockwise direction. So this is anti-clockwise direction is +1. Then here second one is clockwise direction. Then this will become -1. So here the number of encirclement is -1 + 1. So will become 0. So there is no encirclement of this a point A with this closed path. Similarly for this point O, this point and this point, say for example this is 1 and this is 2. So that is in a anti-clockwise direction, that is +1, and the second point is in a clockwise direction. So this will become -1. So number of encirclement will become +1 -1, which is equal to 0. So both points are not encircled. So here the method is very important. The method how I am going to find out is, first one is we need to draw a line or vector from the point where we have to find out. Means from the point which one you are going to determine how many encirclements of this point is there. So for that, from that point you need to draw a vector in any orientation. So the orientation is any way you can write, in any direction you can take it as, okay, and it has to join to the, say for example this is the outside of this closed path. I am just extending this line, assuming that I have joined to this point. Say for example this is D, and say this is for example it is C. So I just joined the outside of this closed path from this point A, from where to which I am going to find out the encirclement. So for this point I'm finding the encirclement, for this point I'm finding the encirclement. Okay. Next, second one, identify the number of intersection. That is what we have taken, 1 and 2. So identify intersections. This is the second step. Identify intersection of this vector. Intersection of this vector with the closed path. That is the second step. Third one is mark this intersection. With arrow. So that is what we have said. See, the first one is, this is in this direction. The direction of this path is this one. So that is I have represented with the arrow, and that is in a anti-clockwise direction, that is taken as positive, and we make it as 1. So mark this intersection with the small arrow on the same vector, means on this line. On this line we have to represent. Next, if the opposite directions, if opposite directions you got, then it will be cancelled. means that's why number of encirclement is 0. The cancel the oppositely directed encirclements, and the remaining arrows gives us the number of encirclements of that point. So the number, you see here, these two have got, so these two are cancelled, both are opposite direction, those two are cancelled. But here if you look at this in the previous example, see here, I have got adding in the same direction, so I have got 2 added. So -1, -1. So -1 plus -1, -2. Here also -1, so I got -2. So likewise, we need to, if there are opposite direction, then we have cancelled here. That is -1 plus 1 will become 0. So there's no encirclements at all. So the remaining arrows we need to, gives us the number of encirclement of that particular point. So here, number of encirclement is 2. 2, and that to be in clockwise direction, because this minus is clockwise direction. So in the closed path which you have discussed in this all these examples, we can find out that is there is one encirclement. Here it is 2 encirclements, and here it is there are no encirclements for this kind of example, right? So likewise we can explain about this number of encirclements. So what is encirclement? Nothing but a point if it is inside the closed path. If I have taken a path, that is tau of s. If it is lying inside the path, that is called as encircled. We can say it is encircled. So how many number of encirclements are there for that particular point? For that particular point means how many closed paths are covering that A. How many closed paths are covering that A is nothing but we are finding the number of encirclement. So we have to find the number of encirclements by using these 4 steps. That is, draw a vector with any orientation or in any direction, and it cuts the closed path at a different intersection point. You have to find out. Then mark those with the arrows, that is with the directions. So that point, from that point, say for example here, from that point, this is going like this. Means it is going in this direction, means it is a clockwise direction. That is why I have represented clockwise direction here. Similarly, here one more point, that is second intersection point is also I'm marking as directions. So with the arrow. Then fourth one is if there is opposite, then cancel each other. But it is not opposite. Both we are going to count it as -1, -1. So n is equal to -2. So there are 2 encirclements for this particular point A. There are 2. I mean, in a clockwise direction. Both paths are in clockwise directions. Okay. So this is the concept of encirclement. So in the next class, we discuss about the third step, that is analytic function and singularities. So first, before going to the Nyquist plot, we need to understand these 5 steps. So first one is pole zero configuration. That is what we have studied, that 1 plus poles of 1 plus g of s into h of s is equal to open loop poles of the system, and zeros of 1 plus g of s into h of s is equal to closed loop poles of the system. So that is what we have studied, and as well as encirclement and counting number of encirclements. So in the next class we discuss about the third step, which is analytic function and singularities.